Hi, everybody. Welcome to this talk about noisy neighbors. I'm going to talk about a new open source collector for noisy neighbors or performance interference. I see some familiar faces from the talk earlier today. There is some overlap, but I hope we'll get through it quickly and you'll hear new material. You might have seen one of the results of some of these surveys. This one was published by Datadog, showing that more than half of the containers that operators run use less than half of the CPU requested for them. So our systems run at relatively low utilization. And if you look at utilization at the well-known large companies, they have reported relatively low utilization. Utilizations between 20 and 40%. We know this because they published this when they talked about their internal orchestrators. And so 20 to 40% seems like industry standard. When I run surveys in groups like this, I usually hear those types of numbers, 20 to 30%, 30 to 40%, maybe half and half. Some people much lower, some people claim to have 50%. And what has happened over the last few years is that some companies have been able to achieve a lot higher utilizations. Google had reported around 35% CPU utilization in 2011, which increased to 50% in 2019. That's 1.5 times. That's a huge, huge increase in efficiency. They were able to get a lot more from their servers. So what happened to make those companies have such higher CPU utilization? And so there are two major contributors that I was able to find. One of them are advancements in vertical autoscaling, which is adjusting the memory and CPU requests for containers so that orchestrators can pack more workloads together. And as in the open source community, actually the cloud native community can benefit from some vendors offering this type of functionality like Perfect Scale, ScaleOps, StormForge, Cast AI, and so on. But the other end, the other contributor, is the ability to sustain good performance as you pack workloads tighter together. When you pack workloads tighter together, they start interfering with each other. And the ability to handle noisy neighbor is really an enabler to getting the higher efficiency. And this is what we'll talk about. There have been dozens of papers over more than a decade from well-known universities and the hyperscalers detailing why this happens and how to fix it. And I think there's enough there that we can benefit in the Linux community and in the cloud native community from these. And I do want you to see the slides. All right, so this talk, I gave another talk earlier today. This talk will focus on the problem itself. So what is noisy neighbors? And how do I actually have it in my own system? Why should we care? And we'll dive kind of motivate, is this an important problem to solve? Then go through some of the solutions that companies have reported to have and what we can do about it, and then talk about our collector and what we're doing with it now. I did my PhD in noisy neighbor mitigation, specifically network noisy neighbor mitigation. I started a company that built network observability tooling using eBPF, and we later sold that company to Splunk. And I'm still a maintainer on the OpenTelemetry network collector, which we contributed. And I'm now focused on solving the noisy neighbor problem generally. So let's see what noisy neighbors are. We run cloud native applications. We run these containers or pods on Kubernetes, or we run kind of whatever orchestrator you're running in Docker Compose. Ultimately, these run on physical hardware, and applications need to share the physical resources that the hardware offers them. When one application uses more than its fair share, then other applications cannot cannot use that resource, and so their performance degrades. And in this talk, I'm going to focus on the last level cache and memory bandwidth. How does cache noisy neighbor look like? Your application is laid out across the memory hierarchy. You have different working sets of different intensities, and those live in the different areas of the cache and main memory. So in this graph in purple, you can see the blazingly hot working set that lives in L1, closest to the CPU. And then the hot, warm, and cool working sets live in L2, L3, and DRAM. When a noisy neighbor comes in, it uses the shared last level cache very aggressively. And so it evicts your application from L3 cache. And now your application, to access its warm data set, cannot go to L3. It has to go to DRAM, which is slower. In the more extreme case, the noisy neighbor runs on the same physical core as your application. It's another hyperthread on the same core. And it evicts your application from L2 cache as well. So now even to access the hot working set, your application has to go to DRAM. And if you look at the access numbers on the top, L2 and L3 are a lot faster than DRAM. Could be 50 times or more faster. And so, theoretically, applications should run much slower on when there is noisy neighbor. So do they actually run slower? Google ran this experiment on their production workloads, where they ran synthetic noise generators that generated a lot of memory bandwidth and a lot of cache interference on these production services, and found large slowdowns. So for example, web search is the Google search node. They found 5 times slowdowns in the face of noisy neighbors. ML cluster is a machine learning text classification system. They found, again, around 5 times slowdowns in the face of noisy neighbors. And memkeyval is an in-memory key value store like memcache. They found up to 14 times degradation in performance. So these workloads are kind of synthetic workloads, and they look like big data analytics, kind of very aggressive in using resources. Does this actually happen when you have interactive workloads? And so at MIT, they ran this experiment. They ran memcache alongside a garbage collected workload. You can see on the top graph here, as the experiment runs, memory bandwidth is relatively low. And as the garbage collector starts, when the mark phase kicks in, memory bandwidth saturates, reaches close to 100%. If you look at the latency, the P99.9 latency, it is relatively low at 50 microseconds. But then as the mark phase begins, the latency spikes up by 3 orders of magnitude, 1,000 times. So you don't really need to have these big data workloads running alongside you. Even garbage collection can be a noisy neighbor. And if you're running systems that sometimes have large transactions that have to touch a lot of records in memory, those can be noisy neighbors as well. But still, this is kind of a synthetic experiment, right? It's very constrained, just these 2 workloads working in tandem. It's very engineered. Does this happen kind of more in general when you run workloads and when you run interactive workloads together? And so to answer that question, we deployed the OpenTelemetry demo, which is a demo system that comprises around 20 different services written in 11 different programming languages. So we ran this on a machine, and we load tested it so that we can start seeing interference between the different components. And so to see how the different components interfere, we measured CPI. CPI, or cycles per instruction, is an important metric used in these different papers to see how efficient the CPU is. The idea is this: you take the number of cycles that your application is running and divide it by the number of instructions. Right? The instructions is what your program wants to run, and then the cycles is the time that it actually took to run it. So if you need to execute some number of instructions, if there's a lot of interference in the memory subsystem, the CPU is going to have a lot of these stall cycles waiting for memory. So running those instructions would take a lot of cycles. So the CPI is going to be high. If there's low interference, less stall cycles, then the CPI is going to be low. And so what we did is we measured the system and we compared the CPI when there's high memory contention and when there's average memory contention, and we compared the two. And these are the results we got for the different components of the system. Most of the components experienced 20 to 30% slowdowns in CPI. So they actually took more cycles to execute when there was high contention. And some of them took up to 3 times slowdown. So this is actually impacting. It seems like it would actually impact real systems. I mean, take it with a grain of salt. This is a demo. It's a demo system. It's not a production system. But this gives us some hint that this would be happening in your production. But should we really care about it? Is this important? Well, consider this. To illustrate this, I simulated a system, 2 systems, one under high load and another one under low load, with these events. So the system with the low load would have fewer of these saturation events, fewer garbage collections. The system under high load would have a lot of them. And so if you look at them intuitively, if these saturations cause slowdowns, intuitively, the high load system is going to have a lot more slowdowns. So users are going to have a worse experience under high load. And so intuitively, as operators, we know that when the system is highly loaded, and we've been trained over many years, that systems under high load have low performance for users. Users suffer from high load on our system. So what we do is we scale out our systems to run them at lower load, so lower utilization. So let me say it another way. High load causes high memory contention, causes low CPU efficiency, which causes us to breach our SLOs. And what we do is we scale out, so we run at lower load. And I want to claim that this is an anti-pattern. We shouldn't do this. This is wasteful and ineffective, because we just end up with a lot of systems running at low utilization. Instead, if we can ensure that this contention for memory doesn't hurt the CPU efficiency, doesn't hurt performance, then we'll be able to run at higher utilization and still keep the performance that the users expect. And if some companies are able to achieve it, why shouldn't everybody be able to achieve it? Now, this is not only about reducing costs so that you can scale down. If we go back to these graphs, think about it. As we scale out our systems and we move from high load to low load, we're kind of reducing the load just enough so that if we're measuring the 95th percentile, we're making sure that the 95th percentile is reduced. But what about the 96th percentile? Right? Like, we're just pushing the problem out. Our users are still suffering less, but we haven't solved it. And by solving the performance interference, we'll be able to solve those problems for the higher end percentiles as well. So this is also about user experience. Okay, so what can we do to measure and mitigate noisy neighbors? So consider this. If we can only find the 5% of containers or applications that cause the most of these saturations, that cause most of the time slowdowns for the other applications, then we can do the following things. One thing we can do is we can adjust memory resources. So one failure mode of garbage collected systems is that if you allocate too little memory for them, then the heap size that they get to process transactions becomes very small. And now the garbage collection has to work very frequently, very hard in order to clear any memory so that future transactions can go ahead. If you just increase the memory for those systems, the garbage collector would work a lot less hard, so the performance of all of the other services would improve, which is great. And just knowing where you have the problem can help you out. The other thing you can do is you can find the application applications that have bad memory patterns. So you could have applications where developers decided to scan memory in order to answer requests rather than use a hash table or a sorted tree in order to look up the results. And that could be a very good trade-off, take some tech debt, but if it hurts the other workloads on the system, is something that maybe you can go to developers and ask them to fix it. So just knowing what pods, services are misbehaving could help you solve this. And if you can't do that, you can at least run those systems on separate hardware. So those systems that are generating a lot of noise, they should suffer from it, but not everybody else who's well behaved. And then all of the other services at least run with good performance for the users, except these that you isolated. So you can do a lot just with observability, just with having a collector that shows you this behavior. But you can solve this automatically as well, which I'm excited about. This is kind of an extra, an extra functionality you can build with the collector is to automatically mitigate. Because some CPUs support directly controlling the amount of cache and memory bandwidth that each workload receives. If your CPU doesn't support that, you can also place your noisy neighbor, pin it to a core far from everybody else, right? Like one core, and then reduce the frequency of the core. So it has less opportunity to do damage. So those are the two mechanisms you can have in order to throttle down noisy neighbors. So containers should do this, right? Everybody says, I get this question a lot. Containers contain, so why wouldn't they isolate performance as well? The answer is they just don't today. We should build this. The C group subsystem doesn't support this, but there is support through another subsystem in the kernel called resource control. And I gave a talk earlier today about how to extend that to make these automatic mitigation systems possible in the kernel. So what you would do is you would find offending applications using a lot more than their fair share, and then restrict them, use these mechanisms. And in fact, both Google and Alibaba Cloud published that they already have such systems in place. Google published as early as 2013 that they had a system in place to mitigate noisy neighbor using CPI across all of their shared infrastructure as of 2013. And Alibaba Cloud published that as of 2020, they had been running a system like this for over 2 years on an order of 1 million cores. So. No reason why we shouldn't build these for everybody. Now, the problem of building a collector for noisy neighbor is that the events that cause noisy neighbor happen at very short timescales. So here I simulated a system where you have, garbage collection takes between a millisecond and 100 milliseconds. So I simulated those types of events here. And you can see if you sample the memory bandwidth at 10 millisecond granularity, you're able to see these events. But if you then sample those same events at 1 second, all of the signal is lost. You can't see anything, you can't do anything about it. So we set out to build a collector that measures memory bandwidth every millisecond, which is very different from what we have in other systems, in other observability systems, right? Like where you get the 15-second aggregations. So let's talk about the collector. We want to collect metrics at 1 millisecond granularity across all of the CPU cores. And ideally, we would have timers that fire every millisecond. But what happens in practice is that we have something more like this. There's jitter, right? And so we ask ourselves the question, how much jitter are we going to have with the timers that are available to us? We used high-resolution timers with eBPF and wanted to know, is it going to work? So here is a benchmark with high-resolution timers on a system with 96 cores. And in the graph, you see a vertical line between the fastest core to answer and the slowest core to answer. And the scale on the y-axis is microseconds. So you can see all of the cores answer within mostly 5-6 microseconds. We wanted to see under workload, are we still, this is a system without any work being done. If we stress test the system, is it still going to behave well? And could we get timers to fire at 1 millisecond intervals? And so here, kind of this summarizes the results. This is a residual log scale survival function graph. I'll show you the results. I'll interpret them for you. We ran, I think, 7 or 8 of the kernel stress tests with stressed NG. And we found just one test where the performance is abysmal, which is the lock test. And I don't expect your systems to work under that type of workload. Even there, half of the 1 millisecond intervals were OK with, I don't know, 20 microseconds of latency, but half of them were terrible. But even under the other stress tests, we found that 99% of these 1 millisecond intervals had less than 50 microseconds of jitter between the fastest core and the slowest core answering the timer. So this is totally reasonable for a 1 millisecond aggregation. It's a 5% jitter. So you get your results to within 5%. But on the regular workloads where you run kind of CPU-heavy workloads, you're getting 99.99% of these intervals with under 10 microseconds of jitter, which is amazing. So this is completely, it seems like this would be a completely feasible approach. So how does this data look like? Here is 1 millisecond samples of the OpenTelemetry demo per process over a 500 millisecond interval. You can see here something's happening, right? The OpenTelemetry collector for, 30 milliseconds has a high rate of cache misses. This is cache misses. So memory bandwidth, this has to go to DRAM. And if you put this graph on the top here and look at the overall, the total number of cache references, so this is the hits plus the references, you can see that around the same time, there was a decrease in the total goodput of the system, right? The system wasn't able to, the CPU wasn't able to achieve the same, to read the same amount of memory during that period of time. So if you know the memory management system, this is kind of a thrashing behavior where you kind of keep pulling in data into the cache, but you're not doing as much good, effective work during that time. The stage where the project is at right now is that it collects these raw 1 millisecond measurements and writes them out into a Parquet file that we now analyze. But very soon we hope to have these algorithms that can attribute these noisy neighbor behaviors. They can say, okay, in this 1 millisecond interval, was there a noisy neighbor or wasn't there, and who was the noisy neighbor? Once you do that, then you don't have to have the raw data, the 1 millisecond data. That's too much data. Nobody wants to look at this data, and it's too big for Prometheus or the other observability dashboards. You want to have a summary saying what fraction of time each pod or process was noisy neighbor over. Now you can aggregate over 15 seconds or 60 seconds, and the data makes sense. Another thing you can do with the 1 millisecond data with detection is to run these automatic mitigations. Because once you know, okay, I know that in this millisecond there was a noisy neighbor, now you can restrict it, limit the amount of resources it can use. So that is next steps. We benchmarked the collector to have under 350 megabytes of memory. And a big concern is CPU utilization, right? Like you're getting kind of data almost at, not almost, exactly at every context switch and at every millisecond for every process in this live system. So on the bottom here, you can see the total number of millicores used by the workload, and on the top, the number of millicores for the collector. The workload goes up to around 30,000 millicores, so 30 cores, and the collector goes up to around 250 millicores. So that's 0.75% of CPU. There's also some eBPF overhead. We measured that at around another 0.75%. And we believe we can optimize it 2x. But I want to make the point that if this data helps you solve the memory noisy neighbor problem, then this overhead is completely acceptable. And even higher overheads are OK. Think about it. If somebody told you that you have a service where the average response times is 40 milliseconds, and I'm running this system, it will increase the average to 42 milliseconds, a 5% increase, right? That's a lot. But then I can reduce your P95, the 95th percentile latency, from 250 milliseconds down to 75 milliseconds. I think a lot of operators would tell you, yes, that's a great trade-off, let's do this. So even a 5% overhead would be acceptable if you're able to solve the noisy neighbor problem. And of course, we're not planning for 5%. We're planning for well under 1%. You can deploy this today. We're publishing container images for x86 and ARM. And there's a Helm chart if you want to deploy this on Kubernetes. Right now, you have to give it your S3 compatible bucket, so S3 or GCS and so on. And you can give it a quota if you don't want to overwhelm your storage, and it supports storage quotas. And you can read more about it in the project's README. The project is hosted on GitHub. It's under the Apache 2 license. And I'd like to invite all of you to join and contribute. We're doing the work. It's a cool project. It's in eBPF. The user space component is built in Rust. And we're building these benchmarks. And we want to have more noise generators that users can run on their systems to benchmark those systems and how they behave with noise, similarly to what I showed the Google results earlier. We need help kind of analyzing the raw data in order to create good detectors. This is in the coming weeks. I don't think we'll have it. I don't know if we'll have it many months in the future, but if this is something you want to do in the next few weeks, then please join us. And if you just feel like running the collector and want to give us feedback, we'd love your help. We have the contact details in the project README, and I hope this will help the community reach the better performance that we can see from some companies and have it wildly accessible for everybody. And like the meme of the dog in the burning room, this is fine, noisy neighbor, this is fine. I hope we can avoid this, this kind of being in this bad environment and kind of fix our environments. And with that, I want to thank you for listening, and I'm happy to take questions. Henrik.
One question. So I saw in the Helm charts you're using S3 buckets. Can I use mini-IO instead of S3? Or do I force to use S3?
Yes, the question is, does the system require the usage of S3 buckets, or can you use other S3 compatible storage like min.io? Yes, you can use other compatible storage. It doesn't require the URLs. You can specify the endpoint as long as it complies with the S3 protocol. I've been using it with a vendor that's not S3 or Google.
And the other question, if I deploy it on the same cluster as my where the noise happens, would that have an impact?
So the question is, if you deploy this on machines on a cluster where you have noisy neighbor, would this have an effect? I think is the question, is this going to cause noisy neighbor by itself?
Yeah, so just the mini-IO storage.
Oh, would it be, so if you're running it on a system that's running min.io, will min.io be noisy neighbor to your other workloads or to the collector? That's a great question. If you want to find out, install it and tell me what you find, or I'll help you. I'm happy to help you kind of look at the scripts. The repository has all the scripts to analyze the Parquet files. You can do it yourself. I'm happy to help out. Just reach out.
Is this the same behavior when you have resource limits for CPU and memory activated? Like you see the noisy neighbor problem in that scenario as well, or we're assuming that that's without that being in place?
So I think the question is, I'm sorry for paraphrasing, but wouldn't CPU limits solve the noisy neighbor problem? It turns out that you can have pretty low CPU utilization, but still have a lot of damage that you create. So a lot of our systems are not very memory intensive, but if they suddenly go into a memory intensive phase, they can do a lot of damage. So CPU limits by themselves don't help you solve the problem completely. But what you could do is if you detect that one of your components, one of your applications is going into this phase where it's really noisy, then you can change its CPU weight, which is, if you know, in Kubernetes, when you have CPU requests, then when when your workloads don't have limits, when the CPU saturates, the scheduler divides its resources based on the requests, which are these, you get these CPU slices. But if you adjust your slices, then you could have a similar effect to pinning the workload and reducing the frequency. So that could be a solution, but I think that you'd want to have a system that dynamically adjusts those limits, because otherwise you wouldn't divide resources according to kind of fairly between your workload when this doesn't happen.
I assume you're saying the throttling issue that comes about with the request and limits, which is why you're saying that we need to dynamically scale it up and down, right? The throttling that might happen if you have the request and limit.
Yeah, sorry. The question is, when you have requests and limits, then you get this throttling. That type of throttling could be helpful, but if you look at how the limits are implemented for CPU, it's very step function-y. It's very on and off. So it lets workloads burst and then throttles them very aggressively. So that would still let them be noisy neighbor. It's not the right mechanism to solve this, but really these types of CPU scheduling and kind of descheduling some workloads could be some solution, but you need to solve this carefully. So the question is, could noisy neighbors contribute to high CPU throttling in some cases? I think so. I mean, it depends on the case, but you can think about if you have a noisy neighbor, it reduces the efficiency of all of the workloads running on the system. So for the same amount of load, now they use a lot more cycles, and that could cause them to hit throttling. And I guess that would decrease the performance of your services even more, right? So it's a double whammy. Good question, thanks. Yeah.
Do you have any estimate on how much data the 1 millisecond consumes on Prometheus, wherever you're storing?
So the question is, how much data does the collector produce with the 1 millisecond granularity? So, and you mentioned Prometheus, but this is going to parquet files into object store. So how big is that data? So we've found that it depends on how many cores you have, how many processes you're running, and so on, because it's per process, per core data that it's writing out. But I think we found, and the repo has benchmark data, and I'm trying to pull it from memory, but you can think about 2-3 megabytes per second on a very busy large system. So this gets to fill up a gigabyte relatively fast. So you want to have a quota, and if you set it to a gigabyte, I think you can get a few minutes of runtime, which is probably more data than you need in order to understand the dynamics of your system.